Hey everyone, ready for another deep dive? This time we're tackling something truly mind-blowing. High-energy cosmic rays.
These things are wild. I mean, when we're talking about particles with energies beyond anything we can even create in a lab.
Like way beyond, right. I mean, what we're talking about today makes the Large Hadron Collider look like a kid's toy.
Pretty much. And for years, we've known these particles existed, but figuring out where they come from has been a huge challenge.
Right, like it's not like they come with a return address, haha. So where do we even begin to untangle this cosmic mystery?
Well, it starts with understanding what cosmic rays actually are.
Okay, so Cosmic Rays 101, what are we dealing with here?
At the most basic level, we're talking about charged particles, mostly protons and atomic nuclei, zipping through space at incredibly high speeds.
And when we say high speeds, we're talking like a significant fraction of the speed of light, right?
Oh, absolutely. These things are moving so fast that they carry insane amounts of energy.
Okay, so we've got these supercharged particles flying around. How do we even detect them?
Well, there are two main ways. One is using space-based detectors, like instruments on satellites. The other is using ground-based observatories.
Right, I remember reading about the Pierre Auger Observatory in Argentina. It's massive. It uses these huge tanks of water to detect the faint light produced when cosmic rays hit the atmosphere.
That's one approach. But there's another really cool observatory that's been making waves lately. The H.E.S.S. Observatory in Namibia.
H.E.S.S, tell me more.
It stands for High Energy Stereoscopic System. Basically, it's an array of 5 giant telescopes that work together to capture the light produced when cosmic rays slam into our atmosphere.
Ah, so it's like a cosmic detective using a magnifying glass to look for clues.
Exactly. And recently, a team of scientists using H.E.S.S. made a pretty major breakthrough in understanding these elusive high-energy cosmic rays, especially those electrons and positrons exceeding 1 tera-electron-volt.
Whoa, hold up. Tera-electron-volt. For us non-astrophysicists out there, what does that even mean?
Think of it this way. 1 tera-electron-volt is 1,000,000,000,000 times more energetic than the light we see with our eyes. That's a lot of energy packed into a single particle.
Yeah, okay, that puts things into perspective. But if these cosmic rays are so powerful, why has it been so hard to find their source?
That's the real puzzle, isn't it? You see, these things don't travel in straight lines. They get deflected by magnetic fields that are, well, pretty much everywhere in space.
So it's like trying to trap a pinball bouncing around a pinball machine, except the pinball machine is the entire galaxy.
A very chaotic pinball machine. And to make things even trickier, space-based detectors are relatively small. So catching these high-energy cosmic rays is kind of like trying to catch raindrops in a thimble.
Right, and I imagine ground-based detectors have their own challenges too, right?
Oh, definitely. They have to sift through a constant barrage of lower-energy cosmic rays, kind of like trying to hear a whisper in a hurricane.
So how did the H.E.S.S team manage to make this breakthrough? Did they build a bigger thimble or find a way to quiet the hurricane?
Neither, actually. They used a combination of cutting-edge technology and some seriously impressive data analysis techniques. They analyzed 10 years' worth of data from H.E.S.S. using algorithms to sift through all that noise and isolate the signal of these high-energy cosmic ray electrons.
10 years? That's dedication. So what did they find after all that number crunching?
Well, this is where things get really interesting. They discovered a sharp drop-off in the number of cosmic rays at the highest energies. And that, my friend, is a major clue.
A clue. Okay, I'm officially intrigued. What does this drop-off tell us?
It suggests that the cosmic rays we're seeing, the ones with these insanely high energies, they probably come from just a few very powerful sources. And here's the kicker. These sources are relatively close to us.
Wait, hold on. We're talking about something in our cosmic neighborhood. This is getting good.
Oh, it gets better. Because now the question becomes, what kind of objects in our galactic backyard are capable of launching particles with this much energy?
Okay, now you've really got me hooked. I'm ready to meet these cosmic suspects. So we've narrowed down the search, right? We're looking for a few incredibly powerful cosmic accelerators relatively nearby in our own galaxy. What kind of objects could possibly fit the bill?
Well, when it comes to cosmic powerhouses, there are a few prime suspects. One possibility is pulsars.
Pulsars, those rapidly spinning neutron stars.
The very same. And they are seriously extreme objects. We're talking about the remnants of massive stars that have collapsed down to a size smaller than a city, spinning hundreds of times per second.
Okay, yeah, that's pretty intense. But how does that translate into launching these super energetic cosmic rays?
Well, it all comes down to the combination of their incredibly strong magnetic fields and their rapid rotation. They
Mm.
create these powerful electric fields that can accelerate particles to, well, pretty much the speed of light.
So imagine like a cosmic blender, but instead of smoothies, it's whipping up high-energy particles.
That's a pretty good analogy. But pulsars aren't the only contender. We also have to consider supernova remnants.
Oh, right. The leftovers from exploded stars, those are definitely powerful events.
The powerful is an understatement. When a star goes supernova, it releases an almost unimaginable amount of energy in a very short amount of time. And those shock waves that ripple out from the explosion, they can accelerate particles to incredible speeds.
So even thousands of years after a star explodes, its remnants are still causing all sorts of mayhem in the galaxy.
Exactly. And that mayhem can create the conditions needed to produce these high-energy cosmic rays. But there's another type of object we have to consider, and these are the real heavyweights of the universe. Active galactic nuclei, or AGNs for short.
AGNs, the supermassive black holes at the centers of some galaxies. Now, those are some seriously powerful objects.
We're talking about black holes millions or even billions of times more massive than our sun. And as they gobble up matter, they release these enormous jets of energy that can extend for thousands of light years.
So these jets are basically like cosmic fire hoses blasting out high-energy particles.
It's a pretty wild picture, isn't it? And AGNs are definitely capable of producing the kinds of energies we see in these high-energy cosmic rays. However, remember that drop-off that H.E.S.S detected? That tells us that the sources are probably relatively close within our own galaxy.
So while AGNs are cool and all, they're probably not the culprit in this case. But that still leaves us with pulsars and supernova remnants. Those aren't exactly rare in our galaxy, so why haven't we pinpointed the exact sources of these cosmic rays yet?
Well, there are a couple of reasons. First, even within our own galaxy, there are vast regions that are still poorly understood. And second, those pesky magnetic fields that we talked about earlier, they make it incredibly difficult to trace the paths of these cosmic rays back to their source. It's like trying to follow footprints on a trampoline.
Yeah, that sounds like a pretty tough challenge. So, how do we go from knowing these particles exist to actually finding the specific objects that are producing them?
Well, it's a multi-pronged approach. Scientists are constantly gathering more data, both from H.E.S.S and other observatories. They're developing more sophisticated algorithms to analyze that data, and they're working to improve our understanding of those magnetic fields that make things so tricky.
So it's like a giant cosmic puzzle, and with each new piece of information, we get a little bit closer to solving it.
Exactly. And by understanding these extreme environments that produce these high-energy cosmic rays, we're not only learning about some of the most fascinating objects in the universe, but we're also pushing the boundaries of our understanding of physics itself.
Okay, that's pretty cool. But before we get too lost in the mysteries of the cosmos, let's bring things back down to Earth for a moment. Why should we, down here on our little planet, care about what these high-energy particles are doing?
That's a great question. It's easy to think of these cosmic events as something distant and unrelated to our lives, but these high-energy cosmic rays can actually have a very real impact, even here on Earth.
Really? In what way?
Well, for one thing, these high-energy cosmic rays can pose a risk to our technology, especially anything we send into space.
Ah, okay. Yeah, I can see that, like, satellites and spacecraft are pretty vulnerable out there.
Exactly. Those delicate electronics can get fried by a single high-energy particle. It's like a tiny invisible bullet packing an incredible punch.
So it's not just about understanding these cosmic rays for the sake of knowledge. It's also about protecting our technology.
Absolutely. And the potential impact goes even further. These particles can actually interact with our atmosphere, potentially influencing things like cloud formation and even lightning strikes.
Wow, so these cosmic rays are literally shaping our world.
In a way, they are. But perhaps the most profound impact is on our understanding of the universe itself. By studying these cosmic accelerators, we're peering into extreme environments that we could never replicate here on Earth.
Like they're natural laboratories for physics?
Precisely. They push the boundaries of what we know about matter, energy, and gravity, giving us insights into the fundamental laws of the universe.
It's like having a front row seat to the most extreme physics demonstrations the universe has to offer.
And who knows what future discoveries await us? Perhaps by understanding how these cosmic accelerators work, we'll unlock new energy sources or even new ways to travel through space.
Okay, now that's getting me really excited. The possibilities are pretty mind-blowing.
It really is a reminder that we are part of something much bigger than ourselves. And the quest to understand these cosmic rays is ultimately a quest to understand our place in the universe.
Beautifully said. Well, I think we've covered a lot of ground today, from those initial confusing signals to the realization that incredibly powerful objects are flinging particles around our galactic neighborhood.
It's been quite a journey, hasn't it?
It has, and it's left me with a sense of wonder, not just at the incredible power of these cosmic rays, but also at the ingenuity and dedication of the scientists who are unraveling their secrets.
I couldn't agree more. It's a testament to the power of human curiosity and our drive to understand the universe around us.
Well said. So, to everyone listening out there, if this has sparked your curiosity, don't stop here. Keep exploring, keep asking questions, and who knows, maybe you'll be the one to make the next big breakthrough in unraveling the secrets of these powerful cosmic rays.
And remember, the universe is full of mysteries just waiting to be discovered.
Until next time, keep looking up and keep diving deep.